All right, yeah, thank you for the introduction. This talk was actually created by Amir, Amir Ayupov. He unfortunately couldn't get visa on time, and he stayed at the States. I'm just delivering the content, but I'll be happy to answer questions at the end and yeah, walk you through the tutorial. This is about adding a pass to Bolt. Bolt is a binary optimizer that is part of LLVM. And let's show the slide of what it actually represents and what platforms it supports. Bolt stands for Binary Optimization and Layout Tool. We take out the binary, break it into pieces, combine again, and using profile information, make it faster. That's the main idea behind Bolt. It currently works on ARC64 and x86 64 platforms. If you apply Bolt, for example, to clan, in this case, built without PGO, you can see double digits improvements. So if you build something, build system like, let's say, Chromium, you can get several minutes or save several minutes on your build time. And exactly how Bolt does it is not the purpose of this talk, but I still quickly will explain that it reads profile information either through LBR or through instrumentation, and then just changes the code layout. Believe it or not, executing the same code, the same instructions, but organized differently in memory can improve your performance a lot. We can also use Bolt for other purposes. Since we already have a rewriter, we can do instrumentation on transformation, we can do spectrum mitigation, and some people use Bolt for reverse engineering. So why would you want to add a Bolt pass? And there are maybe multiple reasons. Several, probably not on this slide. You might have a better idea what to do with it. I know, for example, in the past I tried to extend the functionality of memory sanitizers because if you're familiar with sanitizers ecosystem, they work at IR level, so they need to instrument at IR, which is a big advantage, but also disadvantage because you cannot see inside assembly code. So if you want to instrument assembly code, you need to either manually insert instrumentation, or you can use something like Bolt. So adding the Bolt pass for sanitized instrumentation will be something very, very practical. But you can also add more optimizations, and you can use Bolt as a binary analysis framework. So what internally Bolt does, it has several passes in its pipeline. And before we get to optimization, we obviously have to discover functions in the binary, discover data objects. And we have to disassemble these functions. But disassembly is not something complex, like ObjDump can do it. After that, we have to build CFG. So we have to do more analysis and find out branch destinations. For direct branches, it's very trivial. It's a little more tricky for jump tables. But since we're mostly dealing with compiler-generated code, not handwritten code, we rely on several heuristics that work for us in like almost 100% of the cases. If we do an optimization, we have a special step there where we have to read profile, and we have optimization, which consists of several passes, but this will be the focus of this tutorial, how you can actually do either optimization or transformation pass. Once the pass is complete, we emit the code and rewrite the binary. So for example, if you decide to rewrite the function, you can actually rewrite it in existing binary and overwrite some of its instructions. So before going into details of implementing a pass, let's look into Bolt IR, because this is what we'll be working with. And this picture shows LLVM IR next to Bolt IR, although it's not, you shouldn't compare them directly because Bolt IR is very low level. it operates on MC instructions with some extensions. But if you look at the binary, we represent it with a binary context, which is a set of binary functions. So, and every binary function is further consists of basic blocks, each of which consists of instructions there. It's kind of obvious, but worth mentioning. And here we have a slide which compares different representations in LLVM. So bolt.ir is something new, I would say, although it's not used, let's say, by Clang, at least not yet. I think in the future it might be possible to actually emit bolt.ir just to make some of the passes easier and to convey more information to both through the compiler. But I would say bolt.ir is somewhere in between machine AI and MC level, because MC itself is just every function there is just a set of instructions. There are no basic blocks there. You cannot do complex analysis on it. And at some point we were thinking, can we raise binary to a higher level? And in some cases, yes, you can. You can go as high as LLVM, but if you're focusing on just performance optimizations, then it becomes not very practical. So in the best case, we probably can do it for raise it to machine AI level, but then there's also several implications that, such as frame analysis, that don't work like in 100% of the cases. So our internal representation we call MC plus because we extend MC instruction. It is well, mostly it's target dependent, but it allows you to do data flow analysis. And I will include, or Amir has included an example later in this tutorial. So to operate with MC plus, we have a class called MC plus builder. And there are several examples here what you can do with instructions that you cannot do with regular MC instructions. And the most important one, it's kind of like a building block of MC plus, is you can attach arbitrary piece of information to MC instruction. And this could be like either data flow analysis or like extra information. For example, if it's indirect jump and it's a jump table, this is, with annotations, we can attach this information to instructions. So I already mentioned jump table information attached to instruction, but there are other examples. For example, like tail call, conditional tail call, where you have jump on condition to a different function, right? This is easy to detect, and internally we convert conditional tail calls into condition instruction and then the regular call, but at the end of the process we actually emit the optimized conditional tail calls. For C++, it's important to attach exception handling information for call instructions, so they become what we call internally and what they're called at the LLVM level invoke instructions. And of course, like you can do data flow analysis. So for this tutorial, let's design a simple peephole rule. And the goal will be to do something more or less real and convert existing instruction of 0 in the register on x86 into a different one. If you're a bit familiar with x86, there are multiple ways to do basically the same thing, and 0 in the register is one of them. So here we have 4 different instructions that will 0 EX register, and some of them are better than the others, especially if you look at the size of the encoding. I'm not sure how many of you are familiar and can like make a call which will be the best from the code gen perspective. Anyone? XOR. Yeah. So XOR is that's a good call because if you look at the byte representation, it's 2 bytes compared to what 5 bytes for move. And subtraction is kind of similar, but not all hardware recognizes as an idiom. So it's better to issue XOR. And this is what we're going to write the path. So we'll look for the sequences of move 0 to AX and convert them to XOR. How do we do this? We can add a new path, but we start with modifying the existing one, because we already have a path that calls MC plus builder shortened instruction, and it's already x86 specific, so it has access to all target information. So we modify the existing file, or we add this code, basically checking what was before, and if the operand is 0, we can convert it to XOR. It's rather straightforward. Once we do this, we can actually run it on existing applications, but before we want to run it on something big, let's do a quick run of tests. I'm not going to run tests now because I don't have Amir's laptop, but I have a slide showing like what happened when we run Bolt test suite with the new path. And once you actually run it, one of the tests that lives, one of the binary tests that live on the external repo, it crashes. Which could be not so surprising if you know what's the trick there, but let's pretend we are puzzled and we have no idea what's going on. Why the clang, in this case, used as a test case, not to compile anything, but a test case, it crashed. So we have a script that will do most of the hard-working job of like looking for the bug for you, and it can bisect the function in the binary, in the clang binary, that actually caused the crash, because Bolt can apply its optimization selectively. So you can, say, apply to just like half of the functions, and then break down. You can pass it the list of the functions that you apply optimization to. And again, it's all done by the bug counter script. Once it finishes its work, it will actually give you the name of the function that crashed. So there you go. This is an example. You run the hunter, and it gives you the name of the file. So once you know the function you want to look like, what happened to it, and we can look at it after every transformation. So there's a special option called print all. Even if you add the new pass and you don't have a special option to print to dump function after it, the print all will still do it for you. And then you can also pass the specific function name. So that's once we pass the name of the function, it will display what's going on, and you can see what happened before and after shortened instruction pass. This is the pass that we have modified. And as we expected, right, there was a move 0 to the register, and we modified it with XORing it with itself. But as you can see, like the instruction at the bottom is a conditional move, and the semantics of the instruction depends on E flags. So XOR, unlike move, actually modifies the x86 E flags register. And this is something that we should have expected, but we kind of like were in a hurry, like doing this quick tutorial. So the test failed, and we haven't thought about it. So what are we going to do? Like, we can actually leverage the existing analysis in Bolt and see if E flags will be live after the modified instruction. But before we do so, let's produce a test case, because we want to test once we finish our work, right? Once we add the data flow analysis, we want to make sure that the existing test works as expected. But we have to produce it, right? And we have a special option that assists you in this. It's called awesome dump. You pass it the name of the function and the output file, and it will produce nicely looking assembly output, which you can use in a test file. It, as you expected, probably wouldn't work for every function, right? Because some of them depend on external data. But for simple stuff, even with jump tables, it will produce the working assembly. So now we want to add a real pass, not just modify the existing peephole optimization. How do we do this? We have a directory with existing passes. We call them binary passes, not to be confused with LLVM passes. And we call our pass EuroLLVM, so we create a new file, which is the child of binary function pass. And all we have to do is define these three methods. But the main of these three is, of course, run on functions, which takes binary context with the list of functions as its parameter. So this is run on functions is where we're going to do all the important work. And of course, we have to register our pass, which is rather straightforward. You just add it to binary pass manager file into the run all passes. Of course, we want to, like, compared to the simple peephole, we want to add the analysis. And this tutorial includes an example how you can leverage the data flow manager class with its liveness analysis. This is the code, and as you can see, it's pretty simple, right? You just take the binary context from the function, and you run liveness analysis, and you create the instance. And before modifying the instruction, all you have to do is ask, is that flanks register live? And if it's live, you simply skip it, right? Otherwise, you replace with the EuroLLVM with the XOR instruction. And this is very straightforward, except when you run on a really large files, you probably want to run it in parallel because some executables, they have close to 1 million of functions, and running them sequentially could take some time. So, and if you have, let's say, multi-core CPU, why not use it? This is done with parallel utilities that are built on top of LLVM parallel infrastructure. So we have a walk function that takes as a parameter one of the scheduling variants. In which case, in this case, it's a linear to the number of instructions. And this defines how this pass will be scheduled on multiple cores. Important thing to note here is that if you're going to do memory allocation, we don't want different threads to conflict with each other. So you have to pass the allocation ID, which will be used by data flow memory manager. All of this is included in this example. If you want to look at this offline, you will get all the details. So once we add this, we can test this on a simple test case. Now you see that the test passed, and interestingly, it actually removed or replaced 465 instructions and saved over 1 kilobyte of code. And this is the real binary. Although it's an old Clang binary, I believe it's Clang 6, it's still quite impressive. Not sure if it runs faster, but it definitely became smaller. So if you want to continue to look into more complex functions and do the analysis on them, you can do so in the text output, but it gets more complicated with all control flow graph dependencies. To assist you in this matter, we support dump in dot format, so you can dump every function in, and then look at it, let's say, in the utility. But what is more interesting is that you can actually generate dynamic HTML and interact with it and see it in beautiful colors. So there's a tooltip code option that you have to add. And as you can see now, the control flow graph looks much prettier. So thank you. That's the end of the tutorial. We have a lot of time left, and I would like to answer your questions. What do you have? Also, we have, you can, if you don't have a question now or you want to delay it, you can ask it on Discord, on Discourse. We also holding office hours once every month, every second Wednesday, which happens to be today, in a couple of hours. So the 11 a.m. is Pacific time. I think it's 7 p.m. I don't promise to be there, but I'm pretty sure Amir and Rafael will be there. You can also check the community calendar for more information and to actually map this 11 a.m. to your time zone. All right, thank you again.
Thank you for the talk. Does anyone have any questions?
Thanks for the interesting talk. So I would like to know, do you have any numbers for the real world application where Volt has shown some improvements?
I'm sorry, you would like to know the applications?
Any real world applications where Volt has shown some uplift?
So Clang is one of the examples, right? It's one of the open source binaries that is quite large. But from open source, you can probably think about MySQL, the database applications. Python, I think, is slowly adopting Bolt. Amir also tested it on Chromium. At Meta, where we work at, we run it pretty much on every big binary, except for ones that are heavy on the back end. So everything that depends on your CPU front end that suffers from a lot of instruction cache misses and ITLB misses will benefit from Bolt. And by a lot, there's no like exact number there, but the guideline is, let's say, when you have 30 iCache misses per 1,000 instructions, you can expect serious gains from Bolt, maybe close to 10%. You will still get gains even if you about like 10 iCache misses per 1,000 instructions, but maybe a couple percent. Yeah.
Thanks.
Yeah.
Anyone else?
Hi, thank you for the talk. When it rewrites the ELF file, does it have any input additional like linker script or something to decide which text to use for certain input text sections, or it assumes just single text for the whole program?
Well, so we don't use linker, right? We operate on the binary post-link. We ask for the linker though to save relocations from object files, so they help us with analysis of the binary. we have a mode that when we operate without relocations, but it's not as efficient because we have to conservatively assume that function pointers will be stored somewhere in data section. So when we rewrite, we have several modes, like without relocations, you can rewrite functions in place if they are small enough to fit in the original space. But with relocations, we will create a new text segment where we'll dump the new text with all optimized functions, where we are not constrained by typical limitations. We are still constrained by, I would say, the code model. We don't want to get out of 2 gigabytes for code and data, because otherwise we will have to deal with performance penalties or find a way to solve those. But yeah, for now, we are not dealing with binaries that I mean, when I say binaries above 2 gigs, I mean the code and data. Debug information can be much bigger, of course.
So if I would like to use this framework for like an embedded target where pretty much every placement is controlled by a linker script, I should then maybe dump everything into assembly and reassemble and relink?
It depends on what your goals are. Like why use a linker script? Is it because something target specific, like you want it to be at several others? Yeah, I think then you will need to teach Bolt to output. Or actually, one way to do it is to preserve the current layout, to do optimizations in place, although the benefit will be limited, right? Because when we break out the binary, we break every function in basic blocks, and then we separate hot from cold. And when we rearrange everything, the hot segments or hot parts of functions, they go together, while the cold are moved away. So if you have some requirements for addresses, this will most likely break your assumptions, right? That's the whole idea. But if you, let's say, preserve function boundaries, you don't move them around, you can still rearrange basic blocks within every function and still do the separation and layout. So you can still get like benefit from iCache optimizations.
Thank you.
Okay, we have 20 more minutes. Please keep questions coming.
So thank you very much for this talk, and I'm going to have to watch the video afterwards and try and understand it when I go a second time. And I apologize if I've misunderstood here.
Yeah.
But this is an issue where we've had a bit of a look, not before Bolt existed, at how you solve the problem of dealing with optimizations that only become apparent after you've linked. Now, one class of operation, which I think applies to ARM, and certainly would apply if you did this to RISC-V, is when you want to load an address, you load the upper bits, and then you load the lower bits. And of course, these are all symbolic, and they have relocations associated with them. It's very common that though you may be loading 2 different addresses, their upper bits are the same. So once you've linked, you can see that you can get rid of a redundant load of the upper bits. You can just reuse it a second time.
Exactly. Yeah.
The problem is when you do that, get rid of that instruction, you shuffle all your instructions up, and everything moves. And potentially, your upper bits have now changed.
Yeah. So if these are addresses of instructions or functions, yeah.
Is there a way to sort of do you have to do backtracking, or have you thought through that, how that problem will be addressed? Because I'm not sure how bad it is in ARM, but in RISC-V, you end up, if you don't do this, with code littered with dummy moves and even dummy no-ops.
Yeah, I think that's an interesting problem. And if you let's say focus on data addresses, right, which you don't modify, you can certainly run this optimization. Once you deal with code, I think you probably can do iterative approach, like try this, if it doesn't work, like backtrack, try again in the new place, and it's kind of going to be slow. I'm not sure if it's worth it. It's not a problem on x86 as you've seen, right? Because the address feeds into instruction. That's the big advantage of CISC architecture. But yeah, on ARM, I personally haven't looked much into ARM or RISC-V optimizations, but that sounds like a good idea for these architectures to try and build.
Thank you.
Thank you.
Thank you for the talk. What happens if the change you do in the binary changes which registers you use? So can you replace what registers an instruction is using? So in other words, can you do register allocation again, or are there any plans to support that?
Yeah, you certainly can't change registers, and if you want to preserve the semantics, like you have to rely on analysis. Obviously, doing register reallocation is something more complex. I mean, there are like simple cases, right? But if you want to completely relocate registers in your function, for example, because you have a new profile, right, and you want to move all spills and reloads on the cold path, then I don't have a good answer. I think one way to do it is to actually try to race to machine instruction level and use LLVMs, register locator, with the new profile information. But we can probably try something lighter weight, but the benefits, yeah, I'm not sure. Like you'll have to implement basically the register allocator in this case. But certainly, yeah, there's certainly some potential there.
And since we have time, maybe I'll ask a second question. Yeah. Would Bolt be a good framework to do binary instrumentation? So in the sense that I have my binary and I want to start, instead of relying on LLVM for instrumentation, I want to do it directly on the binary.
Yeah, good question, because we were also thinking, like, can we do this? And we actually did this for a number of reasons. A couple of years ago, we added to x86 because we wanted to see, like, can we, right now we rely on, or we were relying on perf with LBR data, which is sample-based, it's not precise. And the question was, like, can we do better with a better profile? We were looking into Intel P-trace, or processor trace capabilities that actually gives you the much longer history. But the slowdown was too much, and we ended up implementing instrumentation that right now is used. You can use it to produce the profile that can be fed later to Bolt. And there's also implementation for ARC64 that we'll see in open source soon, hopefully. But I think there are other reasons to do instrumentation. Sometimes you want to see the call graph, and there are utilities outside Bolt that allow you to do this. For example, Valgrind with its tools. The problem is that Valgrind does it kind of like dynamically. So the overheads, if you have a huge application, the overheads can be significant. Bolt does the instrumentation statically, and then when it executes, sometimes it's faster. I'd say like several times faster than Valgrind. So if you want to focus on generating call graphs, Bolt can be used for that.
Yeah, and I'm also thinking that cases where Valgrind doesn't support what I want, maybe I want to measure certain things, or I don't know, like trace the address is accessed by a program, and I was wondering if Bolt would be a good tool for.
Oh yeah, absolutely. So please reach out to us like for more details.
Okay, thank you.
Thanks.
Okay, any more questions?
Hey, thank you for the talk. You said that you only support ELF binaries, is that right? What about Microsoft PE binaries? And if you don't support these, how hard would you think it is to extend the support?
Yeah, so ELF is our primary format. Actually, ELF64 is currently a page for review to add support for 32 ELF, but unfortunately does it during the build time. We do have support for Mac O, which doesn't help you, but I still want to mention it because it was implemented and we played with it, but haven't really used it. For PE, I think there's interest. So we're happy to guide you how to add the support. But yeah, we like Meta, at least right now, doesn't have plans to add it. Maybe in the future. Okay. But it will be interesting. Yeah.
Okay, thank you.
Thanks, Maxim, for taking on so many questions.
I think there was more question. Like that, yeah.
Yeah, we have time.
Yeah, I just wanted to ask really quick. So regarding debug information with Bolt, is it generally a priority in Bolt to preserve or be able to preserve debugging information? And if so, is it all very automatic, or does a parse writer potentially have to account for that?
Yeah, with debug information, it's important for us to preserve it because we use Bolt in production. So we update Dwarf, and it's currently the longest running parse and also the parse that takes most of the memory. Because if you look at the binary, let's say the binaries we deal with, they have 500 megabytes of code, which is a lot, but the Dwarf that comes with it could be like 5 gigs, and we have to update it. If we stick to our standard optimization, the code layout, it's relatively straightforward. We don't have, for example, change inline functions or call sites. It's mostly function boundaries. Well, obviously we have, if the function was contiguous in memory and we break it in fragments, so we have to replace its address description dies, right? And the same for sub-programs, for modules. And then update line number information. But once we start doing inlining, right, we run into this limitation. Can we actually squeeze die into the existing sequence in Dwarf? And if you dealt with Dwarf, it's a pain, right? It's designed as a very kind of compact format that is. The main goal was to make it small, not necessarily easily modifiable. So we work on the new Dwarf rewriter that operates quite differently. Instead of updating, we kind of like read all debug information and convert it to LLVM's internal data structures, which are much easier to work with, right, to modify. And at the end, we're going to like speed out Dwarf. We support split Dwarf as well, which in theory should make it easier to parallelize debug info update. But yeah, well, right now it's work in progress. I mean, the new Dwarf rewriter that is kind of supports more modifications. But if you stick to just like basic block and function reordering, yeah, everything should work. But to give you an idea of overheads, it's like for, like, say, 100 megabyte binary, it takes maybe less than 1 minute for Bolt to run through it and optimize it. but debug information update can take maybe 5 minutes. So yeah, like makes it 5 times as slow.
Thank you.
Okay. Do we have any more?
Well, in case you're wondering, we also update C++ exceptions because we are one of the few companies, big companies that use C++ exceptions in prod. So yeah, it's also important. But of course, exceptions are not as big as Dwarf.
Any more questions? We still have a few more minutes.
Is there any passes around thing on de-optimizing? So, for example, if I have code that's stored in AVX and I want to run on a system that only has SSC.
Mm-hmm. Well, we don't have plans to do it. If the question is, can you do it? I guess you do. If you don't have enough registers, you can always probably like extend your stack, save something, and implement AVX using non-AVX instructions, non-vector instructions, if that's the idea. But yeah, that's I think another application of Bolt where you have some hardware features that are not available, or may not. Sometimes it's hardware where the feature doesn't work as fast, and if you're looking at like third-party library that you don't have sources for, you cannot recompile, or something in assembly, yeah, Bolt will be like a good tool to hack with the binary and achieve your goals.
Thank you.
I might have misunderstood, but you're only doing static analysis?
For the binary analysis, if you refer to control flow graph recovering, then yes, we don't use dynamic information. But if you look at the profile, yeah, it will be like dynamic information. So which we don't use for producing the control flow graph, but we use it for annotating and optimizing. So, for example, if you look at the binary with Bolt profile and you look at this assembly, we will actually annotate let's say you have an indirect call, you will have an information about all calls that were there and how many times they were called. And same for jump table targets. So you will have this information there.
Okay, thank you. Any more? All right. Maxim is going to continue the second talk as well.
All right, thank you for your questions. All right.